Hello everybody, in this video we'll be discussing about significant figures and everything related to that. Before diving into this video, you can surely check the previous playlist which was about unit and dimensions, and we have completed 5 lectures and completed that whole chapter, or small part is left. So this is part 2, you can treat it that way also. So today's topic is significant figures. So let's start with its definition. Significant figures. Digits in a measurement. So you measure something and tell me a value. So digit in a measurement about which we are absolutely sure, or you can also say certain. Sure means sure. So you give me a measurement. Okay, I ask you for the length of this board. You measure it and say it is 1.23 meters. Okay, so I ask you, are you sure about this one? Yes, I am sure, I measured it. You'll say okay, so I'll say this is significant. Then I ask you, are you sure about the 2? In this 2, you measured it correct? Yes, you say yes, I am sure this is 2. Let's remove this 3. You measured it as 1.2. Okay, so now what if I ask you for the next decimal place? Tell me the next decimal place. You'll say I didn't measure, I am not sure about it. So yeah, so these two figures become significant, but this is a two-way talk, right? I have to ask every time, are you sure about this? So are you sure about this? So we are going to dive into some rules. So those rules, even if you write a number, I'll come to know how many significant figures are there in that particular number. So we need to learn some rules, after which we can directly, by seeing a number, we'll come to know what are the number of significant figures in it. So if you want to note down the definition, you can go ahead and note down. Okay, now let's go for the rules. What were the rules about? So the rules for counting, or I'll say rules of counting significant figures. So you want to count how many significant figures are there in a particular number. So I'll use the short form. Let's use sigfig. Okay, significant figures. It means significant figures by using that short form. So rule number 1 of from the constitution of physics. Okay, so it says all non-zero digits are significant. Okay, so in a given number, if you don't find any zero, means that all of them are significant. Let's take an example: 2 3 1 1, 2 3 1 1. So this is non-zero significant, non-zero significant, non-zero significant, non-zero significant. So these are rules, remember them. So what if there was a decimal in between 2 3 1 1? So even that case also it works. This is significant, this is significant, significant, significant. 1921, so that as well. No zeros, so you have 4 significant figures here, 4 significant, 4 significant, even 131. So it's no zeros over here, all 3 of them are significant. So 3 significant figures, 3 sig figs we have. Okay, so now let's go for the rule number 2. This one, first one, is the simplest rule. Now let's go for the rule number 2. What does it say? So it says that zeros, so we went for non-zeros, now let's go for zeros. Zeros between two significant, or let's write it in the short form, significant figures, sig fig. So zeros between two sig figs are significant. So zeros between two significant figures are significant. So let's take 2002. Okay, So 2 is significant, it's a non-zero. This 2 is also significant, it's a non-zero as well. See these two zeros. These two zeros are squeezed between, so they are in between this 2 which is significant. So these two zeros are between two significant figures, right? These two zeros are between two significant figures. So they are significant. So this is significant as well. What about decimal? Same thing, 3.012 will take. Okay. So this 3 is significant, 1 is significant, 2 is significant, all are non-zeros. Now this 0. This is squeezed between 3 and 1 which are significant. So zeros between two significant figures are significant. So there are 4 significant figures. You can go on and on with the examples. 4.402. Let's take that. So this is 4 is significant, 4 is significant, this 2 is significant. Now this 0 is sandwiched between, you can say it's squeezed between those two non-significant numbers. So this 0 also becomes significant, right? So easy examples. Where do I keep this? Okay. Zeros between two significant figures are significant. Zeros between two significant figures are significant. So for today's class, I want you all to note each of these rules down, because after this you might forget it. So sit with a pen and a copy. Okay. So what was the third point? Zeros between. Now what about the zeros that are ending? So we are discussing the zeros only. So trailing zeros, or a fancy name for ending zeros. So ending zeros are only, so pay attention here, it's only significant if they come after a decimal. Okay, so let's take an example for this. 2.02. Okay, no, 2.0. Okay, so this ends with a 0, so we are going for the ending zeros. 2.0, and it also comes after a decimal. So only those, okay, I'll take one more example to make it more clear. One is 2.0 and 200. Okay, so 2.0, this 0, this 2 is significant. Okay, this 0 is, it comes after decimal and it's the ending 0, so it satisfies this condition. It comes after the decimal, and it's the ending 0, so it is significant. This number is also ending in 0, so but if you see, there is no 2 is significant, but here there is no decimal place. Okay, and pay attention to the word only. So ending zeros will be only significant if they come after a decimal, not anyway. Like 3000 won't be significant. Okay, only 3 will be significant from there. These zeros are not significant since they don't come after a decimal place. But sir, why is this so? Like, why is 2 different from 2.0? Like this has two significant figures and this has just one. Okay, so why this injustice? Okay, so let's think about it. Okay, so I ask you for measuring some length. Okay, so I give you something to measure, and I ask you and your friend to measure it. So one of you reports 2 and other reports 2.0. So look at this. This has I'm explaining the reason why this is significant. Okay, so you measured 2 and I ask you for the next decimal and you'll be like, no, I am not sure about it. But let's go to your friend now. Your friend has said 2.0. Okay, I said 2. You're sure about it? Yes, he says. Then you go for 0. Are you sure about it? Yes. And then I ask him about the next decimal, which he is of course not sure about, so he has not written that. But see, he is sure about 2 digits, right? he knows he is more closer to the answer, right? He knows he is more closer to the answer. He is more closer to the accurate value, I mean. So that's the idea behind treating this 0 as significant. Or I I hope you got that idea. Yes. He is more accurate, he is more closer to the answer. That's why we treat this 0 as significant. Now, you can look this in the opposite way as well. So if I say, okay, I'll make a statement here. You say if it's true or not. More the number of sig fig, which is significant figures, more is the accuracy. Am I right to say this? More is the accuracy. Am I right if I say this? Think about it. So yes, this has more number of significant figures, this number 2.0. It's obviously more accurate, right? So remember this statement. This is not a rule, but this is a golden statement, if you want to call it. More the number of significant figures, more is the accuracy. So they might give you a question having three options and ask you for the most accurate one. So you have to select the one which has most number of significant figures. So more the number of significant figures, more is the accuracy. Okay, hope you got that idea why this 0 is significant and this is a golden statement. Okay, let's go for the rule number 4 now. Okay, sir, we did zeros which were in between, sandwich zeros, this ending zeros, now beginning zeros. No, unfair, sir, unfair. Okay, the fourth one is about powers of 10. We'll see the beginning zeros as well, so it's just a special case. Okay, let's come back to fourth one, which is powers of 10. Powers of 10, or it has a fancy name which is order of magnitude, whatever you want to call it. So powers of 10 or order of magnitude are not significant. Oh, not significant. Okay, so note it down. I hope you're noting it down every time I write a rule. So 2.3 into 10 power 3. So by this rule, powers of 10, so this thing, powers of 10 are not significant. So this number, if I ask you for the number of significant figures in this number, so there are 1 and 2. You need not count this. Powers of 10 are not significant. One more example I want to give you is this one. Whatever you can take, minus also will. So power is basically power of 10. So okay, here also this is 3. I am using both of those now. So this is 3. Yeah, non-zero, significant. This 0 comes after a decimal, significant, but this is a power of 10, not significant. Let's take one more example now. 30.0. What do you have to say about this? Now we'll use all these 3 rules. Okay. Yes. So we'll use all the 4 rules for this. Quickly try it if you want to know how far you have got the concept. Okay, let's go for it. 3 is a non-zero, significant, 1 significant figures. Now this 0 we can't say anything for now. Let's go to this 0. This 0 comes after the decimal. The zeros coming after the decimal are significant, so this is significant. Now you can look at this 0. This 0 is squeezed between 2 significant figures, so it also becomes significant. How did we go about it? Okay, this is power of 10, so this is not significant. We have 3 significant figures. Let me repeat it for you. 3 significant. So first we said 3 is a non-zero. First rule, it says it is significant. 0 comes after that. This 0 comes after the decimal, significant. This 0 is squeezed between two of those I'll say significant figures. Rule number 2, 0 squeezed between two significant figures are significant. So all of these three are significant, and by rule number 4 this is not significant. So you're getting the idea. Every time they'll add more and more composition, so you have to use all the rules that you study. These are not the only 4. Now, what about numbers that begin with a 0, 0.041? Okay, we can decide the fate of this 0. Okay, it depends. It's a squeezed one. If you see, you'll say, okay, this is significant, this is significant. But sir, what about this? So some reference books state it as a different point. If you want me to say it, I'll say it in a second. But I want you to picture this in the form of this. Okay. Now I'll state the statement for you. If a number is less than 1, okay, if this number is less than 1, so the zeros to the left hand side of the first non-zero are not significant. I repeat the statement. If a number is less than 1, the zeros to the left hand side of first non-zero number are not significant. So by that rule, if we go through that rule, I'll give you the hack, but before that, okay, so zeros to the left hand side of this first non-zero number is our 4, so left hand side are not significant. So this is not significant, this is not significant. So since I gave you a decimal, it was something tough to conclude. If I have given you this number 0420, so then you'll say, okay, what is this 0 useful for? You'll just drop it, right? Wise decision. So there are only 3. But I wanted to confuse you with the decimal. Okay, that was the rule. Make sure if you want to note it down, note it down. But now let's try to visualize this through this one through the 4th rule. Okay, what will I do? I will shift this decimal to 2 places. So can I write it this way? Yes. Okay, those who don't know, if we shift the decimal to the right hand side, we raise the 10 to the power the number of shifting. So I shifted once, shifted it twice, so I raised it to that power. Okay, now you count. This is power of 10, insignificant. 1, 2, significant. Here also we had got 1, 2, right? So you always have 2 ways of picturing it. So it should strike you at very first when you see a number less than 0. So go for this. Convert it in terms of powers of 10. You just remove the zeros till you get the first non-zero number. What if you had like this 0.402? Okay, now let's move. Let's convert it to this form, 4.02 into 10 power minus 1. So I took it to the right. Don't move it to one more. You can, whatever. 10. So this power of 10 is insignificant. Now come back to this. 4 is significant, 2 is significant. This 0 is squeezed between 2 significant figures is also significant. Okay. Now let's quickly go for rule number 5. This is a very simple topic, but students tend to forget it. So I am reminding you again and again to sit with a copy and a pen. Okay, so let's go for the rule number 5. So while changing units, number of sig fig, which are significant figures, remain same. This is a very logical point. So this point is very logical, the point number 5. So because see, if you measure something in meters and then convert it to centimeters, will it get more accurate? No, obviously not. So accuracy does not change, significant figures won't change as well. Okay, So when you change unit, you have to be careful that you maintain the same number of significant figures. Like let's take for example 3 kilometer 0. Okay, first let's take 3 kilometer. Now those who know SI prefixes will directly say 3 kilometer is 3000 meters, and then you have to check for the significant figures. So here we have one significant figure which is a non-zero. Here let's check this. This 3 is significant, these 3 zeros are not significant because there is no decimal, right? Zeros, only trailing zeros, ending zeros are significant only if they come after a decimal. Okay, so these 3 are not significant. So one significant figure, one significant figure. Everything is going well. But what if I had said 3.0 kilometers? Increased accuracy. Okay, so there are 1, 2. 0 is after decimal, significant. Now you would have said the same thing, 3000 meters. But have you fallen for the trap? Yes, because see, here there are 2 significant figures. Here, one significant figures, these 3 zeros are not significant. So what to do now? To create the same thing here, sorry. So you say 3 into 0. So you have 2 significant figures and less others you express in the powers of 10. 10 to the power 3, 3 zeros, so 10 to the power 3. And here you have your 2 significant figures. Wise way, okay? So you have to be careful whenever you change units, don't change the number of significant figures. So rule 5 is also done. Let's go for the final rule, which is rule 6. Rule 6 says that constants or pure numbers or constants, okay, have infinite constants have infinite number of significant figures. Sir, why is this so? So suppose example, okay, pi equals 3.14. Okay, suppose this was the accepted value. I know there are other decimal places as well, but they have given you that pi is 3.14, but you are sure about that value, right? You calculated it through somewhere, through mathematically somewhere, obviously. So you are sure about its accuracy. You know that pi is something that is very accurate and we know it to many decimal places. So you can keep on adding decimal places, right? You can go on adding the other decimal places. You might know it. Okay, go on adding it. So all of those becomes significant, right? So, and even other examples if you want. So pure numbers, basically any constant. So let's say speed of light, which was 299792458, maybe I'm not sure, or I don't know. Okay, so let's assume it's this in meters per second. So this 1 2 3 4 5 6 7 8 9 9 significant figures. No. So you can add a decimal point and go on adding 0 0 0 0 0 0 infinite numbers of significant figures, right? You are sure, you know that the speed of light is this much. It cannot change. Okay, so if you are absolutely correct about certain value, so that value has infinite number of significant figures. Constants have infinite number of significant figures. So this should be actually rule 1, because whenever you get a number, look if it's a constant. They'll provide you the information that this is that. Suppose they provide c is the speed of light and this they give this value. And then suppose let's take one more example for this. Refractive index of water. So they have given you refractive index of water is 1.33. Yes, I guess. So yeah, so they have asked for significant figures. Don't say it's 3 1 2 3. No, you can go on adding zeros since it's a constant. Okay, you are very sure about the value. So when you are very sure about the value or you know it's a constant, then constants have infinite number of significant figures. Okay, do you want to note it down? No, you should note it down this time. No choice, I'll give you. Please note it down. A humble request, I'll say. Okay, let's just revise it once now. All non-zero digits are significant. If you don't see any zeros in a number, all of them are significant. Zeros between any two significant figures are significant. So you find zeros which are sandwiched between nice sandwich. So nice. Okay, you have zeros between any two significant figures, they also become significant. Trailing zeros are significant only if they come after a decimal. If there is no decimal, they are not significant. Okay, powers of 10 we know are not significant. So, and here a point should click you, right? A point should click you. What is that? A number less than 0. Yes, so you have to check if it's less than less than 1, not 0. That will be negative. So if you have a number less than 1, you are converting it to this format. So I'll add a star over here. I gave you the example something 0.041 something. Okay, so and now this point, if you are changing units, you should keep in mind, don't change the number of significant figures since accuracy does not depend on units. Okay, constants have infinite number of significant figures. If I give you any constant, or if I'm very certain about something, then it will have infinite number of significant figures. Okay, let's remove this out now. And we'll take some examples for counting significant figures. I hope you have noted these points down, because after 2 days you'll forget it unless you practice many and many examples. Okay, let's just take few examples or problems, whatever. So we'll do it. I'll keep on writing the problems. 2 1 2 1 3. Second one is 2.0013. Third one is 2.0 into 10 to the power 3. Fourth one is 0.049. Okay, wait, 0.049. And fifth one, let it be the last one. Okay, I'll give you a question in this place. First you do this. Okay, let's go for this. So all of these are non-zero. 1 2 3 1 2 3. So 3 sigfig significant figures. Here 2 is significant non-zero, 1 is significant non-zero, 3 is significant. These two zeros are squeezed between two significant figures, significant. So 1 2 3 4 5, 5 significant figures, sigfig. Then let's come to this powers of 10. We see it, we spot it, go kill it. Okay, so remove this, no use. So 2 is significant. What about this 0? It comes after the decimal, significant. So 2 significant figures. Finally, so okay, this one, something strikes you. Yes, it's less than 1. So it's less than 1, 0 point something something. So what do you have to do? You have to convert it to powers of 10. So shift this decimal 1 2. So 4.9 into 10 to the power minus 2. So this is not significant. These two are significant. Those who wish to do it through rule, the rule says the I also forgot, the zeros to the left hand side, the zeros to the left hand side of first non-zero number are not significant if the number is less than 1. Okay, So these two are not significant. 1, 2. Two significant figures. So 2 sig. So one more problem. The unit one I'll give. So tell me what is 25 millimeter equal to? Option A. So is it 2.5 centimeter? Okay, I'll say 25.0. Okay. Is it B? Is it 2.50 centimeter? What's the difference, sir? C. Is it 2.5 into okay, 250 into 10 to the power minus 1 centimeters, or is it, okay, I did a mistake, okay, here it is, or D, is it all of the above? Now those who don't know significant figures, which option will you choose? So those who don't know significant figures are likely to choose this option, but we have learned significant figures for the last 30 minutes and we know that whenever we change unit, keep in mind that don't change the number of significant figures. So count the number of significant figures here. So it's 25.0, this is significant, 2 is significant, 5 is significant, 0 as it comes after a decimal, it is also significant, 25.0, okay. Now there are three sig fig. So come here, 2.5 centimeter. Seems right, but check out for the number of significant figures. 1, 2. No, this is wrong. We want 3. Come here. So it's 1, 2, 3. Correct. So this is the correct one. Come here. This, if you see, this is not significant powers of 10, and here it also has 1, 2. So we want 3, so this is also wrong. So B is the correct option. D is obviously not the correct one since these two are wrong. And those who don't know significant figures will strike D, sorry. Anyways, let's move to rounding off now. You can practice more examples of this sort. Now let's go to next topic for the day, which is rounding off. All of them are interlinked, so not kind of topic. So rounding off, we know this is a very basic thing, so we'll directly study it through examples. There are rules actually, but let's learn it through examples. Okay, so the first one, let me check the camera. Okay, perfect. So the first one is okay, I'll write some figures first. 2.319, second one 2.314, 2.3152. Let's go for more. 2.3 1.150, and finally we have 2.3132, I'll say, and 5, okay, and 0. So each of this number is a specially chosen. So let's try rounding off. So what you have to round off till we get 3 sig fig. So till we get 3 significant figures, we have to round up the number. Here we have 1, 2, 3, 4. All are non-zeros. So significant figures are 4. We have to go till 3. So we have to drop one digit. Which one is that? So we have to drop the last digit, which is 9. So whenever we are dropping a number greater than 5, you should add 1 to the previous digit. So this becomes 2.32. We dropped 9, so we increase this 1 plus 1, which became 2. So whenever you drop a number greater than 5, you increase the previous digit by 1. That is the statement if you want. But yeah, you might have known this earlier as well. Okay, so let's go for this now. This number is less than 5, so obviously there won't be any change. You have to add a 0 rather, whatever. That doesn't make sense. So you have to blindly drop it. If it's less than 5, the dropping digit is less than 5, you directly drop it or drop it blindly. 2.31. 1, 2, 3. 3 significant figures, we are done. Now let's come over here. Now these 3 are special. You might have known about this, but these 3, let's focus now. Okay. Now we have to come to 3 significant figures. We have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. Now the rule is that, so suppose now we want 3, right? So 1, 2, 3, 4, 5. Now if you have 5 no, and then you have some digit followed by it. So see, we want 3 significant figures, so we want 1, 2, 3, and we will drop this 2, and that will create some changes, or maybe not, but let's see. Okay, so we want this 3 basically, so we are dropping these 2 digits, this 5 and this 2. Okay, so whenever you have 5 followed by some non-zero digit, so this 2 is a non-zero digit, so you have a 5 and a non-zero digit following it. So whenever you drop such kind of a number, you have to raise the previous number by 1, or you have to increase the previous number by 1. What did I say? If the numbers to be dropped has a 5 followed by some non-zero number, 5 followed by 2 which is non-zero, then the previous number should be raised or increased by 1. So this was 1, we increased it, and 1 plus 1, so 2. Increase it by 1. Okay, so this basically we got it. I'll revise it once later, once we finish. Okay, now let's come to the third one. Now it's 5 followed by a 0. This was for 5 followed by a non-zero. Okay, we want 3 significant figures. We'll end up having some version of this. Okay, so we have a 0 over there. So whenever you have 5 followed by some 0, you look at the previous digit and see if it's even or odd. Now you will know what is even and odd, so obviously. Okay, so you have 5 followed by a 0. 5 followed by a 0, you come to the previous digit. Okay, it's a 1. 1 is odd or even? Even. Oh sorry, 1 is odd, so you add 1. So if it's odd, you add 1. Okay, if 1 is odd, so you add 1. Sorry, excuse me. Okay, so let's okay, I'm fine now. Okay, let's move on. So let's, for 3 significant figures, now this one, so 1, 2, 3. Now watch carefully. This was odd, right? The digit previous to the dropping one. So this is 5 followed by a 0. If it was simplify, that also works. Okay, if it's simplify or a 5 followed by a 0. So this is for both the cases. Or if it was simplify, okay, it's simplify, you're dropping it. If you're dropping it, check the previous digit. If it's even, you don't change anything. Okay, so here it was odd, so you added 1. Here it is even, so you don't change anything, you just drop it blindly. So let's revise this now just in a jiffy. So this 9 was greater than 5, so the dropping digit, I'll say x, the digit which is dropped is x. Okay, so 9 was greater than 5, so you add a number to the previous number, so you increase the previous number by 1. This was 1, so it became 2. 1 plus 1, 2. And then here you come, here you see a 4 over there. So 4 is obviously less than 5. So for numbers which are less than 5, you just blindly drop it. Blind yourself, drop the 4 and paste the other thing. Okay, now come here. Now what if it is equal to 5? Here we have 3 cases in which it's equal to 5. Now you have to check carefully if you have 5 and if it's followed by something else also, right? Here it's 5 followed by some 2 which is non-zero. Okay, so if you have 5 followed by some non-zero thing, so this is 5 followed by non-zero. Okay, in that case, what do? You drop both the digits and increase the previous one with by 1. Increase the previous one by 1 if you have a non-zero digit fall after 5. Okay, now come here. What if it's 5 is followed by 0 or nothing? 5 is followed by a 0 or you don't have anything after 5. Okay, So in that case, you have to look for the previous digit. You have to look for the previous digit if it's even or odd. So if it's odd, you increase it by 1. If it's even, you keep it the same. I know this is a bit difficult to digest now, but you remember this, okay? So if it's, let's write here, if it is odd, so odd plus 1, we'll say odd plus 1, and even, nothing. Even keep same. Odd plus 1, even keep same. Odd plus 1, even keep same. Odd plus 1, even keep same. So this 2 you will be familiar with. These 3 are a bit new to you, okay? So please try more examples if you want to. So let's come to the last part of today's lecture, which will be operations on significant figures. We are including significant figures in operations. What operations, sir? Heart transplant? No, of course not. So, okay. Before I jump to the topic, you guys up for a story? Okay, I'm sharing a story now. Of course, it has a lesson linked to this. Okay, suppose there is a car factory. We have a car factory. It produces, suppose, 500 engines per day. 500 engines. We have 500 body parts, like the outer body. 500 other parts which are required for the car, and but it produces only 100 wheels, okay? So this it produces within a day. So my question to you is, what is the number of cars produced in a day? Significant figures, yes. Okay, but let's come to this. 100 wheels, we'll say the least produced is wheels, so it will depend on that. Good idea. So wheels, each car has 4 wheels. Of course, the car number is 25. So only 25 cars per day, but we had 500 engines, 500 bodies, 500 other parts, but the thing that we lacked in was wheels, and that was the game changer, right? So I want you to get this idea that car manufacturing dependent on the one which had least the part which was least in number, okay? So what does that have to do with significant figures? Or was it my mood to tell you a story? No. So here also, the when we add, subtract, divide or multiply the operations, I mean, on significant figures, the one which has least accuracy will be the game changer, okay? Either least number of decimal places or least number of significant figures, that will be the game changer. So that idea I want you to acknowledge, okay? So the rules for addition and subtraction are same, not rules, just a single rule. Addition and subtraction. So this rule you have to follow when you add two numbers. Okay, so the rule says the result, in this case it will be the sum, your answer basically, the sum or difference should be rounded off, that's why we learned rounding of things. So rounded off to the same number of decimal places as that with least number of decimal places. Okay, you can spot the word here, least number of decimal places. So this is the rule, because when you add two things, when you add them, so as I told you in the factory problem, the things depended on the least part which was produced. Now here also, the one with least number of decimal places or the least accuracy decides the game. So the result, the answer, whatever you call it, should be rounded off to the same number of decimal places as that with least number of decimal places. So when you add okay, I'll give you an example now. Let's say 2.5 plus 3.182 plus, okay, let's just take 2. Okay, so first you add them. 3.182. Okay, this is 0 0. Okay, I won't do that since it's okay. So this is the answer that we get, but we have to follow this rule. So the answer, this one, should be rounded off to same number of decimal places as that with the least number of decimal places. So among this, which has the least number of decimal places? This one. And how many are there? One, just one decimal place, right? One. This has 3. 1 2 3. 1 2 3. You can see it that way also. 182. Okay, and this has just 1. Okay, so your answer, this answer should be rounded off to one decimal place, rounded off to that many as the one with least decimal places. So rounded off. So when you drop to less than 5, nothing changes. 8 greater than 5, change it by, increase the previous digit by 1. So the answer is 5.7 and not this, right? And don't have this habit of rounding off things too early. Like, don't round it off before adding. Once you add, you get the answer and then you apply the rule. Okay, once you get the answer, then you apply the rule. Let's take one more example of this. Okay, I'll remove this. Please note down the rules that we are discussing today. Let's take 2, finally 2, 2.143, 3.16, 4.2. Okay, forgive me if I make any calculation errors. I deliver the content or the concept in through a sense. So 6 plus 4, 10, 1, 1, 2, 3, 4, 5, 4, 6, 6 and 3, 9. So okay, 9.503. Are you reporting this as the answer? No, no, no. So but what do you have to check? Decimal places. So least number of decimal places here, it's just 1. Here it's 2, here it's 3. So you have to see for the least one, like the wheels. Okay, so the least one is this. So you have to round off your answer to least number of decimal places, which is just one decimal place. So you drop 3, 3 is less than 5, no change. 0 also you drop. So it's like 5 followed by, okay, you're not dropping the 5, so keep it as the same. When you drop 0 as well, 0 is less than 5, so that does not make any change. So those rounding of the last 3 type does not mostly occur in your questions. Okay, I hope you can try more examples of this sort, but I'll end the addition subtraction rule here. If you want to note it down, please note it down, and I recommend highly that you take the notes of this lecture. Ta-dang. Ta-dang. Finally, let's go for the multiplication and division rule. Multiplication and division rule. So the result or the answer, in this case it will be a product or a quotient, whatever. So the result or the answer should have as many decimal places. Okay, sorry, the result or the answer should have as many significant figures. Here it's significant figures. So remember that for addition it's number of decimal places, least number of decimal places, and here it's least number of significant figures. Okay, the result should have as many significant figures as the number with least, again in braces, number of significant figures. Okay, the result should have as many significant figures as the number with least number of significant figures. What do I mean by this? Let's take an example. If I say 1.2 into 1.23, around 1.44, it will be whatever. Let's see. Let's do it this way. 2 3s are 6, 2 2s are 4, 2 1 are 2, so 3, and there 2. Okay, 1 2 3 6 7 4 1, so around 144, that is 1.2 into 1.2. Anyways, okay, 1 2 1. I hope you know to calculate this, because you are supposed to calculate. Okay, so let's come to this. Okay, the thing in the previous, like I didn't do it for subtraction, but you can also try it for subtraction. You have to apply the same rule, that is of the it's about a decimal places, least number of decimal places. Okay, let's come back to here. So it's 1.476, but are you reporting this answer? No. You check out for least number of significant figures in multiplication and division. So 1 2 significant figures, 1 2 3. Okay, so 1 2, so you have choices of just keeping this 2. The once you round off, first you should round off, the answer should be rounded off. Okay, so what do you have to report? You have to drop this 6. When you drop 6, it's greater than 5, so you get 1.48. now this 8 you also have to drop, so when you drop 8, it gives you 1.5. so the answer to this, you have to report it as 1.5, because it has two significant figures, which is same as the one with least number of significant figures. Answer should have, or I'll write here, should be rounded off. Should be rounded off to, okay, should have. Just remember behind your mind that it is rounded off actually. No issues in that. Now, what more can I give you as an example? Taking this next one as 1.56. So I've already calculated it for you into 1.431. So it comes out to 2.232360. Okay, so my calculator says this. And anyways, let's follow the rules now of significant figures. Now this number has 1 2 3 significant figures. This has 1 2 3 4. But we are looking for the one which has least, so it's this one, bingo. So let's go for this. So we have to round up our answer to 3 significant figures. So let's try doing it. So drop this 0, no issues. Drop this 6, increase this by 1. So 3 plus 1 is 4. Drop this less than 5, no issues. Drop this, okay, how many we want? 1 2 3. Okay, so drop this as well. So the final answer is 2.23. okay. So can we try division 1? I'll do it on my calculator first. Anything, I'll use 1.23 divided by 1.1. So it says, okay, I have done this. 1.23 divided by 1.1 gives us the answer 1.11. You are actually supposed to calculate this. Okay, I'm not doing the calculations. So okay, so I'm just teaching you how to do this. Okay, so least number of significant figures, this has 1 2 and this is 1 2 3. So this one, so 2 significant figures. So let's try dropping things. 2, blindly drop it. 8, if you drop greater than 5, so this you have to increase by 1, so that gives us 2. Now once you drop this 2, doesn't create any nuisance. Now again you have to drop this, we want 2, right? So again you drop this, that gives you we dropped 8, so which was greater than 5, so you need to put you need to increase the previous one by 1. Okay, now we wanted just 2, so again you drop this and look, what you got. The same thing you got anyways. It means like 1.23 is a square. Actually 1.22 is 1.1 into 1.1, so this you'll get as 1. So just an approximation, okay, or no issues if you didn't get this one. This answer is 1.1. Through significant figures we are likely to get some weird answers. Anyways, so they whenever a question is given, if that it will be specially mentioned if you are supposed to do it through significant figures or normally. If you are asked to do it normally, you don't have to apply these rules. You can go through your own methods, round off anywhere you want, provided you don't make any assumptions, okay, any wrong assumptions. And if they ask you to do it through significant figures, then you have to follow these two rules. I hope you got this idea. That's all. I think, yeah, that's all for today's lecture. If you made it this far, like the video and subscribe to my channel. And as usual, keep enjoying physics.